This video is going to show you a few demonstrations of how we can affect or alter the rate of reaction. Again, I think a lot of this is probably somewhat intuitive, and I suspect you've experienced this before anyway, so I don't think there's going to be anything too new here. The last thing I'll mention quickly is some means that you can use to measure the necessary variables that allow you to calculate a rate of reaction. So why don't we get started right away. So most of these factors that I'm going to show you are by means of video. So you just need to watch the video and again take down some notes if you like as you go. And so here we go. Here's the first video. I'm going to zoom in. So those two demonstrations showed that it is dependent on what type of either element or compound you're dealing with in terms of rates of reactions. The first demonstration showed that two alkali metals, sodium and potassium, do not react at the same rate under the same conditions of temperature and pressure. The potassium added to the water clearly reacted much more rapidly. So that's due to the chemical nature of potassium compared to sodium, and I think you have a bit of an idea why that is. Reactivity due to the larger size of potassium with that valence electron kind of stuck out there ready to react. Potassium, that valence electron is a bit closer to the nucleus, there's a bit tighter hold on that valence electron. The second demonstration was then two elements in the same period, that's potassium and calcium, and even though calcium is smaller in terms of radius, it's clearly more stable because when he added the calcium to the water, the reaction while it proceeded was not that vigorous, whereas again with the potassium, much more vigorous reaction. So the chemical nature of reactants is quite important in terms of reactivity and hence rate of reaction. Let's look at the next one. Just wait. And again, pretty evident, concentration is important in terms of reactants only, not products. Obviously, rates of reaction are dependent primarily on the reactants. So if we change the concentration of reactants, we can alter the rate of reaction. And again, that was fairly obvious. The more concentrated the hydrochloric acid was, the more vigorous the reaction with the zinc. So concentration of reactants, again, another easy way to affect the rate of a reaction. Next. So in this third example, we altered the temperature of the reactants, and in this case it was really just the temperature of the water. Well, you couldn't see it on the video. The more vigorous reaction of the sodium in water was in water that was about 50 degrees Celsius. The slower reaction was at a water temperature of around 8 degrees Celsius. So it's very clear there. Same amount of water, pretty well the same amount of sodium, but the temperature was quite different and the rate of reaction was affected quite dramatically. So that sodium reacting in the hot water looked more like a reaction to potassium in hot water, but that's because the water was warmer. Next. All right. Yep. So in this example, we changed the surface area. Again, that was adding calcium to water. So calcium as a lump of calcium. Pretty evident the reaction proceeded. It was quite slow. You could see the bubbles gas forming though. But when I added the powdered calcium into the water, the surface area was greatly increased. Much more calcium exposed to water, and so the rate of reaction, as was seen, was quite a bit quicker. So surface area, again, an important way to affect the rate of a reaction. And certainly when you think about gases reacting, they typically would have a huge surface area, and so gases tend to react very quickly. Hence a lot of explosions with gases. And finally, so in this reaction, we increase the rate of reaction quite dramatically by adding a catalyst. Now, the hydrogen peroxide actually does decompose basically under normal conditions, but the rate that decomposition is very slow, and it decomposes into hydrogen gas and oxygen gas. When we just look at it as a liquid, it really doesn't look like it's decomposing, but it actually is, just very slowly. The addition of the potassium iodide, that was the liquid that went in the second liquid, clearly acted as a catalyst. It increased the rate of reaction very dramatically, excuse me, as evidenced by the formation of all those bubbles of gas that got caught up in the dishwashing detergent. Was also added there. But again, it was evidence of that catalyst increase in the rate of reaction. And so again, that's a common way to affect the rate. And certainly in industry, that's a very important way to affect the rate of reaction, because time is money. The faster you can get things to be produced, the more money you make. And so catalysts are a huge area of research in industrial chemistry. So that series of videos kind of showed you how you can change the rates of reaction. One last thing I do want to mention quickly is just some methods for determining rates, and basically it's methods that allow you to collect data so you can calculate a rate. And again, a lot of this you're probably familiar with. So one thing we can do is monitor mass. So you have a mass change, but we can also monitor things like conductivity, and by conductivity we're looking at ions in solution. So this can be a good way to deal with precipitates. If you remember a precipitation reaction, you mix two solutions, are mixed, and you form a solid. And that solid is the precipitate. Well, those solutions are ionic. And so in forming the solid, you have less ions in solution. So you can actually monitor a change in the conductivity, the amount of charge in the solution over time. And if you do that, you can get a measure of the rate of that reaction that produces that precipitate. So that's a couple of ways. The other thing you can look at is actually monitoring pH. And so if you have a reaction where there's going to be a pH change, and that's commonly the case when you add a carbonate to an acid, say, you're going to alter the pH of that solution, and you can measure that with a pH meter. And again, from that, determine the rate. You can also look at the formation of a gas. And a couple of things you can look at here. You can look for gas collection, and so that's a volume. So you simply measure a volume, and from that volume you can convert it to moles per liter if you want, or just measure volume versus unit time. And we did that in grade 11 with the UDometers, gas collecting tubes. So you can do an experiment like that pretty easily and get an assessment of rate. And the other thing you can do is, if you have a pressure sensor, you can measure pressure. And again, that's quite useful in a gaseous system, so where you have gases reacting, because you can, based on stoichiometry, have more or less gas being produced over time, and that's going to be reflected as a pressure change. So that's another way to be able to measure a rate of reaction. You can also look at colorimetric changes. And so by this, I mean you look for a change in color. And that's quite common. We're going to look at one of these in the lab. But you simply have to watch a reaction and until there's an obvious color change, and measure time. And from that you will determine concentrations over time and determine a rate that way. But that's a pretty common one, because quite a few reactions give rise to a color change. So colorimetric changes are not that uncommon in terms of measuring rate. And there's other ways, and you can probably think of other ways yourself. Basically, you have to be able to collect some information over time, some data over time. And so any means that you can to collect that data would allow you to calculate a rate of reaction. So that's all I'm going to say about this this sort of information. It's again, as I said, probably pretty intuitive. You've probably come across quite a lot of this before. So that concludes this video.